Our lesson for today is a continuation of what we have discussed last week, the first part of kinetics of homogeneous reactions. And we'll have the second part today. Hopefully, we'll cover everything for today. That way we can proceed with module 3. Okay, let me check. Correct me if I'm wrong. As far as I can recall, we ended with Arrhenius equation. And that is the dependency of the rate constant on temperature. Let me check. So we'll do a little review on Arrhenius equation. And before that, on the terms that are present in your rate law. Just very fast. That way, everybody is refreshed on what we have discussed last week, Monday. Okay, I'll try to have this on slideshow. If it will not project, then just let me know. Okay, so we're, let me check, rate law. Okay, so we're here. Can you see the slide on rate law that starts with the bullet on the rate law would give the rate of the reaction in terms of A as K sub A as a function of temperature and as a function of concentrations. Can you see this particular slide?
Yes, miss.
Yes, miss.
Okay, so that's fine. Now, this is just a review. So you know that your rate law has two terms that are dependent separately on temperatures and concentration respectively. So your rate constant K is dependent on temperature, and your concentration terms here depending on the species in which your rate is dependent on is your concentration dependent term. And we've also discussed that as per Arrhenius equation, this is how the linear dependency of your rate constant is based on the temperature, the absolute temperature. Now this A is what we call as the frequency factor, and in some reference books, it's also represented by K, but it has a subscript of O, so K sub O. In some books, A here is K sub O. It's the frequency factor. Now, E here is the activation energy, R is the universal gas constant. Now, we've discussed as well on the corresponding unit of K and A. And the concentration of K and A, of course, depends on the overall reaction order. Now, we'll go to that later because it's being discussed here. Now, if you could see now in your slide, you have the relationship between the rates based on the species that appear in your stoichiometric equation. And they are related by the coefficients of this species, also as written on your stoichiometric equation. Now, since your species A, B, C, and D here, written in capital letters, have coefficients, small letters A, B, C, and D, when we equate the rates of reaction based on this species, we just simply divide it by their corresponding coefficients. So A for A, or small letter A for A, and small letter B for B, and so on and so forth. We distinguish the species reactants from products by writing negative on the expression of the rate. So in this case, I have written it in the denominator, but it could be written here, class. So you can have it written here, and you take away these negatives here on A and B. Now, if you're going to apply this particular concept on a specific reaction of nitrogen oxide to oxygen, so this is how you're going to represent the rates of disappearance of nitrogen oxide to rates of disappearance as well of oxygen gas to the rate of appearance of nitrogen dioxide. So they were divided by the coefficients of this species in the provided stoichiometric equation. Okay, so this is very fundamental and you should not forget it because it's a cardinal rule in kinetics that whatever is the reaction is, whether it's elementary or not, this particular relationship holds true. Okay, now we proceed. Now, I gave you this particular self-test last meeting. We'll not discuss that anymore because we've discussed in detail already the answers there. Now,
Miss,
yes.
wala siya, Miss, gamot sa next slide.
Okay, so wala naman siya nag-transition. Anyway, so here it is. So we're done with the rate law. Now we go to the rate equation. So the difference of the rate equation and the rate law is that when we speak of the rate equation, it's a differential equation. And it's a requirement for a differential equation to have the presence of a derivative. So as presented to you, our derivative here is in the form of the rate of change of the number of moles of A with respect to time. So it's a d and a dt. That is if the rate of reaction is based on the species A. So this rate class can be written in terms of the derivative of A with respect to time, and we simply divide it by the volume of our system. Now, having this particular representation for the rate, we have now its units in this form. So we can have mole of A per cubic meter per second, or this could be pound mole of A per cubic feet per hour. It depends on the units of this mole, volume, and time in your problem. Okay? Now, there's a note here that the rate of consumption or formation of a species is an intensive measure, and we've discussed that as well last meeting, why it is an intensive measure. So in here, now we write the rate in terms of the two terms in which it's dependent on, the temperature dependent term, the K, and the concentration dependent term, the C sub A. And we can replace now the K here with its equivalent according to Arrhenius equation. So everything was defined in here. Now, as to the concentration dependent term, so this depends on the type of reaction, which is also in turn dependent on the form and the number of kinetic equations used to describe the progress of the reaction. And this has something to do with the mechanism. So we will study that in detail as we go along, as we finish this particular slide. Now, I also discussed to you the very important cardinal rule also is that you should be able to correctly specify the unit of the rate constant based on the reaction order. And this is the way we determine or express the set of units for your rate constant. So it will always have a per unit time unit, and the concentration will be raised to 1 minus n. 1 minus n, where n is the order of the reaction. So it follows if we have a first order reaction, you will have here a 1 minus 1. So your concentration dependent term will be gone, or the unit of the concentration will be gone, leaving you with the unit only of per unit time. That is for the first order reaction. So if it's second order, if it's third order, you just simply follow this formula in the in your answer for your rate constant, because I'm very particular with the set of units you are reflecting on the rate constant. Okay, in the same way that it's very also fundamental that you should know how to reflect such set of units. We've discussed how the activation energy, or we've discussed the importance of the activation energy in terms of when will a reaction start. So it's that needed energy for bond breakage. That way new bonds can be formed. So unless original bonds existing between atoms and molecules are broken down, no new bonds can be formed. If there are new bonds can be formed, there won't be new substances that will be formed. And as such, there won't be any chemical reactions. So it's being explained in here. Okay? Now, it's that minimum amount of energy, that activation energy. Now, we've ended here. I think this is where we ended. We're in using Arrhenius law, expressing the rate constant in terms of the pre-exponential factor and the activation energy and temperature. We can determine the unknown in the problem, whatever that unknown may be, based on using ratios of two given sets of information. So the formula that you will use would look something like this. You can have the ratio of the ln of the rates. In the first part here, you have the ratio of the rates. It could be equated to time. So the problem may give you two sets of rates and two rates and two times correspondingly for these rates, and you may determine one of which. So you may be given one of the rates and the other one is unknown, but you're given the time that is used in facilitating or effecting the recovery or forming the required state of product in your particular reaction. So in that case, you just simply use this ratio. Or you can have this one. You'll be given the rate constants together with time. It could be that, or it could be class that you'll be given the rates and you'll be given here temperatures. You'll be given the time here and you'll be given temperatures, or you'll be given rate constants and temperatures. So all of this being equal, meaning they can be equated with each of the expressions that you are seeing here. So you work your way through based on what is provided in the problem. But in terms of what is commonly encountered, or what's the commonly encountered application of Arrhenius, it's the rate ratio with the temperature. So you have here rate 2 and you have here temperature 2. So since you started with rate 2 here, the first temperature in which you're going to have the reciprocal of multiplied to the ratio of E over R will be T sub 1. Why is that, Miss? It's because it's supposed to be negative in here, as explained to you last meeting. It should be negative E over R from this one. But since we made it positive, so that is why these two are interchanged. But if you intend to place negative here so that you will not be confused, then whenever you have here R2, this will be also be the temperature corresponding for rate 2. If this is R1, so this should be the temperature corresponding to rate 1. But you should not forget that there should be a negative here. There should be negative E over R. But for this two, you can also have ln of t sub 1 over t sub 2 and equate it with this, meaning you're not provided with rates, actual values of rates, but you're given the time it would take for your reaction to finish based on the desired completion or stated completion. It could also be that you'll be provided with rate constant. So it really depends on what the problem gives you. So this is an extension, this 1, 2, 3, 4, 4 equivalent relationship is an extension actually of your Arrhenius equation rather. Do you have any questions so far before we proceed? So that's what we covered last meeting, and we will proceed with the conclusion that could be derived based on Arrhenius equation. And it will proceed with the graphs of the different lines when you have high activation energy and low activation energy based on Arrhenius equation. You have any question? Okay, so I think there's none. So we proceed with, if you're going to plot Arrhenius equation, so you will have ln of k here. So not k, but the ln of the k values plotted on the vertical axis. And you have here on the horizontal axis the reciprocal of the absolute temperature. So this will be your corresponding line rather if you have a low activation energy. And this would be your line if you have high activation energy. More or less, this is your Arrhenius equation. The slope of this line from Arrhenius equation is E over R and has the unit of Kelvin. Now, looking or basing on the different orientation of the low activation energy and the high activation energy lines for Arrhenius equations, these are the corresponding conclusions or findings that could be deduced. Now, the temperature dependency of reaction is determined by the activation energy and the temperature level of the reaction. Why? Because we see it already being dependent on the E and the capital letter T based on the formula itself. Now, a plot of the LNK versus 1 over T from Arrhenius law gives you a straight line with larger slope for large E and a smaller slope for small e. It's a given that it will have a large slope if activation energy is big because your slope is E over R and your E is in the numerator. So the bigger the value of the E, it's a given that your line will have a bigger slope. So if your E is small, your line of course will be having a small slope. Now, number two, reactions with high activation energies are very temperature sensitive. So those with high activation energy are temperature sensitive. Reactions with low activation energy are relatively temperature insensitive. So take note of this. The higher the activation energy, the more sensitive is your reaction to changes in temperature. It's not that much if the reaction has low activation energy. And number three, any given reaction is much more temperature sensitive at low temperature than at high temperature. This is on a general sense. We're not talking about a reaction which has high activation energy or low activation energy. So generally speaking, whether your reaction is high activation energy or low activation energy, take note, it is much more temperature sensitive at low temperature than at high temperature. The fourth is that the value or the frequency factor, K sub O, or that's capital letter A as well, does not affect the temperature sensitivity of the reaction. So your K sub O does not affect the temperature sensitivity of a reaction. Primarily in the sense that for a particular reaction, your K sub O is constant. It's a constant. If you look at the formula for Arrhenius equation, your K sub O rather, is standalone. It's not part of the exponential function where activation energy and temperature is part of its argument. Okay, so it's a constant. Now, so these are the four findings from Arrhenius equation. Now, we'll have this sample problem regarding this particular rule of thumb. So it's stated several times in our main reference book. And let's look at this. So as a rule of thumb, the rate of reaction doubles for a 10 degrees Celsius increase in temperature. And this occurs only at a specific temperature for a given activation energy. Develop a relationship between the temperature and activation energy for which the rule of thumb holds. Now, neglect any variation of concentration with temperature. Then, second bullet here, determine the activation energy and frequency factor from the following. So you are to determine the activation energy and frequency factor based on this set of data. You're given two Ks, two rate constant, and you're given two temperatures corresponding to this rate constant. Now, before we do that, we'll have this rule of thumb first, that for every 10-degree rise in temperature, your reaction rate, what does it say here? Doubles. So your rate of reaction doubles for every 10-degree Celsius rise in temperature. You are to develop a relationship. So meaning you are to write an equation that will depict this particular rule of thumb. Develop a relationship between temperature and activation energy for which this rule of thumb works. Now, how do we do that? So let's share a new screen here. It's my Jamboard because. Okay, so everybody can see the board?
Yes.
Okay,
Yes.
so now we are to determine the first required information. You are to make an equation that will relate activation energy and temperature where the rule of thumb works. So what is that particular rule of thumb? So let's say T sub 1, you have T sub 1 and T sub 2. So T sub 1 is your initial temperature and T sub 2 is your final temperature. And since that particular rule of thumb says that for every 10-degree rise in temperature, so then we can say that your T sub 2 in relation to T sub 1 will be T sub 1 plus 10. Okay, that's 10. Or, yes, 10 degrees Celsius. So whether this one is already in Kelvin and T sub 2 is said to have a 10-degree rise in temperature, then the Kelvin temperature of 1 will be 10 times higher. I'm referring to T sub 2 already. Higher than that of T sub 1. So in here, we could say that if your T sub 1 has an R1, which is represented as this, then it follows that R sub 2 will be in relation to R sub 1 will be what? Anybody? So for every 10-degree rise in temperature, your rate doubles. So in terms of R1, R2 is?
2 hours of 1 minute.
So it's 2 R sub 1. Okay, very good. So 2 R sub 1. Then what do you think should we do next? I have already 2 pairs of information. What will I use? That way I can find what the problem requires, a relationship between activation energy and temperature. So what will I do? Based on what we have discussed so far, how am I going to utilize these 2 pairs of information? That way I can come up with the equation asking for the relationship between T and activation energy. What do we use? What do we do? Anyone? Aina, what do you think should we use, or what do you think should be the next thing that we're going to do here?
Wait,
You're not really going to think very broadly because we have only covered so far the fundamentals. So when you're asked to, let's say, for example, look for something to use, that way we can come up with what is being required. You only think of the things that we have discussed, and even probably the things that you have learned in the past. Nothing so broad or complex. You should not think of something that is complex. So what do you think should be the next step here? What should we do? Okay, let me check. Fritz, I hope your connectivity is okay now, Fritz. What do you think should we do next here? Fritz? Are you there, Fritz? You keep...
Ara, miss.
Oh,
Wait lang gid, miss.
what do you think should be done? This is very elementary, bala, third year, as in, we should not think that it's something complicated. It's something that we have discussed already. What will you do next? Vincent, what will you do? Are you there?
Yes, miss.
So what do you think, what do you suggest should be done next in here?
Use the ano miss? Arrhenius law.
Which particular Arrhenius, the original form or the one in which we have relationships already?
The one we had relationships already, miss.
So can you outline to me how am I going to use it? I'll show to you the slide. You tell me which one will we use, okay? So you will have a guide. Okay, that's the slide. And since you said we're going to use, this is the original form of Arrhenius equation, and you have here the relationships made from this particular original form of Arrhenius. So which one will I use, Vincent? Which equation will I use? Because I have 1, 2, 3. 1, 2, 3, 4. I have so many equal relationships here that could be made out of this equation that is written here. So which one will I use, or how will I use this one?
First, miss.
The first. So you will, what you mean, rates here?
Miss, ang may R kag T, miss.
And then, what will I equate this, Vincent, with?
Equate mo sa dalaw, miss.
This one.
Sa A over R.
Okay,
Miss.
very good. So that's the answer that I'm looking for. Using Arrhenius equation that we have discussed, you have this relationship between rates and temperature. And you can see here that you have the activation energy E. So we're going to use this one to the one that we are trying to solve. So we go back to our board and use the relationship that we have there on the slide. So as suggested by Vincent, so we'll have ln of R sub 1 over R sub 2 is equal to E over R. Now notice that I place here R1 and I have here positive. So this should be 1 over T sub 2 minus 1 over T sub 1. Do you follow? So that's the formula. Okay, now you substitute the information that is provided on the first bullet. You have here R1. And this R2 that you have here is twice of R1. And you have here E over R. Never mind about the R because it's a standalone constant. So your relationship between activation energy and temperature later can have also this particular constant. Doesn't matter because anyhow, it's a constant. So I'll place here 1 over. So you could see here that your T sub 2 in terms of T sub 1 is T sub 1 plus 10. And you will have here, of course, 1 over T sub 1. Okay? You get to cancel the R1s. So you'll have here the ln of 0.5. Okay, 1/2. And you will have here E over R. And let's simplify this part here. So you will have a T sub 1 if I'll have it here. And I will have here minus T sub 1 minus 10. Minus the quantity T sub 1 plus 10. So that should give you minus T sub 1 minus 10. Your denominator will be T sub 1 times T sub 1 plus 10. Okay, so you have that with plus. Now, you can cancel this. And it is ln of 0.5. So what's the answer for ln of 0.5? Can you solve for it? That's the ln of 0.5. It's negative. ln of 0.5.
Negative 0.6931, miss.
6931. Thank you. So you have it equated to E over R. And you will have here negative 10 over T sub 1 times T sub 1 plus 10. Okay, something like that. This is negative and this is negative, so you can have, and you can divide this 0.6931 by 10 further, so that would be 0.06931 equal to E over R, and I will have here 1 over T sub 1 times T sub 1 plus 10. Okay? Now, since the problem is asking for an equation, so let's go back to the problem, okay? Go back to the slide. So this is the slide. Develop a relationship between the temperature and activation energy for which the rule of thumb holds. Okay? So E and temperature, we will relate activation energy with temperature. So based on what we have there in our Jamboard, so this is how it is. Now, how will we write the equation in this case? So it could be E in terms of T, because activation energy actually is dependent on temperature. Or it's better that way. You cannot have T based as a function of E, because you have two terms here for your temperature. That would be quite difficult in terms of an equation. So how would we rewrite our equation in this sense? So we will keep on one side of the equation the activation energy. So that would be the side where the E is already found. So you can have E equal to, that's the activation energy, and you can have this one. You can cross multiply everything in here. You keep the E on this side. So you will have 0.06931 R, because this actually is a group of constant, times, I'll just write it here, T sub 1 times T sub 1 plus 10. So this is the equation that the problem is asking, that will depict the temperature dependency of the activation energy of that particular reaction in which the given set of data is given. So this set of data, excuse me, is the set of data that will relate the dependency of the activation energy to temperature based on the rule of thumb, that for every 10-degree rise in temperature, the rate of a reaction doubles. Okay? So any questions so far? You will have a lot of this type of problems here in kinetics. You will be the one who's going to derive the relationship between variables. But of course, you will be guided by the problem. You will have information to use that. It's not as simple simply deriving something in which you don't have empirical data to use. That way you can derive the relationship. Any questions so far? Okay, so we go to the next. The next one actually is a lot easier than the first, because in the sense that you have already a pair of data to use. Unlike the first one wherein you're going to give an equation and you're going to derive it. So based on the problem that we have, go back to the problem, you are asked to determine the E and the frequency factor based on this pair of data. Okay, so for a rate constant of 0.001, that would be for the temperature 60 degrees, and for 0.050, that will be for the temperature of 100 degrees Celsius. And based on what Vincent suggested to the class a while ago, I know you have already an idea on what particular formula you will use in this case. Okay, so we go back to our Jamboard. Now, based on number 2, what particular equation do you suggest we use? Via. What equation do you think will be suitable for our pair of information?
Ang ln K2 over K1.
So you are suggesting we write here ln of K2 over K1 is equal to E over R. What should
Yes,
I write
yes.
here? What should I write here?
1 over T sub 1 minus 1 over T sub 2.
Okay, 1 over T sub 2. Okay. So I have here an ln, then I'll use the information that is given in the problem. So let's say my rate constant 2 is 0.050, the second, and my rate constant 1 is 0.00. And I will have here E. By the way, class, if we're dealing with SI sets of unit, we use the rate constant, which is in joule per mole. So what particular universal gas constant are we going to use here if we'll have an activation energy which will be in kilojoule per mole? What should be the appropriate R to use? If it should be in kilojoule per mole, what universal gas constant will I use? R. Your kilojoules per...
8.314.
Oh, sige. Si Drex na ang dasig magsabat. So you have here 8.314. So this is this kilojoule already per kilomole or joule per mole? The 8.314. Kindly check because I don't have my...
Joule per mole, miss.
Mole per mole, miss.
so if I have kilojoules, it should be kilomole. Right?
Yes,
Correct
miss.
siya. Sige. Now, for temperature, it should be in Kelvin. So, I will have here 1 over our Celsius temperature equivalent to rate. It should be for rate 1. Our Celsius temperature for rate 1 is 60. So, 60 plus 273, that would be 333. Minus 1 over the temperature for rate constant 2 is 100. So, this is 373. So 273 plus 373 plus 273, so that should be 373. So you will have, this one has a unit of 1 over Kelvin, right? So the per Kelvin here and the Kelvin here will cancel each other, giving you the activation energy value equal to, can you solve for the activation energy? What's the activation energy? Okay, somebody wrote on the chat box 0.01. Let me see. That would be 0.0104, right? 0.0104. Wait, that's my answer. Your answer is, what's your answer?
100,000, miss. 996.07.
So 100,996.07. Kindly check, ha? So this is kilojoule per kilomole. Or you can use joule per mole in that case because both are in kilo. Okay, so 8 based on the rate constant, the universal gas constant, rather, not the rate constant, 8.314. Okay, now how do we determine the K sub O? Anybody? How do you determine the K sub O? What do you suggest we do? How do you determine K sub O? The pre-exponential factor or the frequency factor? Let me check.
U K all over E raised to negative ERT, miss.
You will have A, then E raised to E over RT, right? Because this one, if placed here, negative siya. K sub O, E raised to negative E over RT. So that would be positive in here. Do you get it? Now, what information will you substitute here? Any information that you have, any pair of K and T will be used or could be used. So if you use the pair 0.005, you will have E here raised to the activation energy that you have. So remember, if you're using this set of units, joule per mole, a kilojoule per kilomole to your E, by the way, I will not tell you na lang. I'll ask you later. So you will have here 8.314, the same set of units as this one, and you will multiply it with the temperature for this. The point, by the way, it's 0.050. This is 0.050. Why can't I erase? Wait, Prasa. How come? Why can't I erase? I can't erase? Eraser. I can't erase. What happened? Anyway, I'll just crush this out. This should be 50 class. 0.050, the corresponding temperature, 0.050, the first one here will be this temperature here, the 373. So you'll have here 373. So this is your K, the 0.050 E raised to the activation energy, which we just solved a while ago, divided by 8.314 times 373. The temperature for this particular rate constant. So you will have a corresponding frequency value of 100,996.07. You divide that by 8.314 and 373, and that should be the exponent of the E, and you multiply it by 0.050. Your answer should be 6.965 times 10 raised to 12. Can you please check if the value is correct?
Same, Miss.
Okay. Okay, so this is our value for the K sub O. What do you think should be the set of units for this K sub O? What should be the reflected unit for K sub O? Our frequency factor.
Per minute, Miss.
Y per minute? Y per minute, Rex?
Makuha niya, Miss, ang units ang K, Miss.
Okay, very good. So whatever is the unit for the K, that should be the unit for your frequency factor. So you can see here that your rate constant has a unit of per minute. So it follows that your frequency factor will have the same unit because your exponential function here in the formula of Arrhenius does not have any role in the set of units for the K and K sub O. The unit or the set of units for K and K sub O is again dependent only on what? K sub O will copy the unit of the K, and the unit or the set of units of K is dependent on the what? It's dependent on the, where do you base the unit of the rate constant? Let me check. John Villarosa, where do you base the unit of the K? You base it on the John Villarosa. Albert Villarosa, are you there? Albert, are you there? I have noticed every time I ask a question, somebody gets kicked out of the room.
Nag-chat siya, Miss, sa
Activation
Setbacks.
is, activation means. No, it's not the activation. Your unit or set of units for the rate constant is dependent on the, where is it dependent on? John Patrick Tagle. It's dependent on
Sa R, miss.
sa
R.
sa R. It's dependent.
Forgive them.
Oh my. Where is it dependent on? My goodness. We reviewed it before I started with the new topic. Johan, where is it dependent on, Johan? The unit or the set of units of your K is dependent on?
Sa time, miss.
Sa ano?
Sa T, miss, ang time.
Ezra, where is your rate constant unit or set of units dependent on? Ezra,
Miss,
it's dependent on the, why do you
same kami,
same ka mo ni?
same kami ni Albert, miss. Answer.
Ano answer ni Albert?
Sa activation, miss.
The activation energy. Sino na mamangkot? Sino na lang wala ko mapamangkot? Drexel, where is it? The unit or the set of units of your K is dependent on or based on the what?
Given, miss.
Given what?
Temperature, miss.
Oh. Let me see. Jericho, goro na kick out. Ay, oh, wala naman siya. Iyang connection is poor. Third year, it tells me that you are not focusing when we are discussing. Why? Because we started this lesson today having to review everything first that we have discussed, those vital points that we have discussed last meeting before we proceed with the new topic. The answer to my question was reviewed to you a few minutes ago. The rate constant units are dependent on the what? I'm scrolling down already. Are dependent on the, what do you see there? Based on the
Order, miss.
order. Correct. So not one got it right. It's based on the order. It's good for you because that particular sample problem already specifies the order of the rate constant, which is per minute. Okay? Hinatag yan na, huh? It's per minute. There. What if this is not given and the order of the reaction is to be determined based on how the problem speaks about it? Or what if the order of the reaction is first to be determined by you based on the empirical set of data that you will use? Then that particular set of units or unit for your K is dependent on the order. Okay, let me just check if you can understand this one in just a few minutes. Let's say, for example, I have this. I was wondering why I cannot erase a while ago. Let's say, for example, N is equal to 3. That's the order of the reaction. Can somebody tell me what should be the units of the rate constant if order of the reaction is 3? Any unit for time, unit for volume, or any unit for amount of matter which is small, you can use as long as it's based on this particular slide. That the rate, that the order, or that the set of units of your rate constant is dependent on the order of the reaction. So let me ask you again. If the order of the reaction is 3, what should be the set of units of your rate constant K? check on the chat box. 1 per mole squared. 1 per mole squared second. So I'll go for the next answer, 1 per mole squared second. What about the rest? Can you just type on the chat box what's your take on the set of units for the K? We'll end with this. What do you think will be the set of units of the K if the order of the reaction is 3? So Drexel already wrote his answer here. You may type your answer here as well. Okay, Bia already has written her answer. Okay, 1 per kilomole squared per minute. For Aina, 1 per mole per second squared. 1 per mole squared. 1 per second per mole squared. 1 per mole squared per second. Oh my. I'll tell you what your set of units should be. Your K should have a unit which is per unit time. So let's say your time is in seconds. So I will have it 1 over S because it's -1. Whatever is the unit of the concentration, since I'm using the second, let's say the concentration is in mole per liter, it should be raised to 1 minus n. So I will write here mole per liter raised to 1 minus 3. Then your K should be equal to 1 over second. Now this is equivalent to -2. So meaning this mole is raised to -2 and this liter is raised to -2. So what will be written in the numerator is liter squared and the mole is in the denominator, mole squared. So this would be now your set of units for your rate constant if the order of the reaction is third order. Do you get it? So not one of you got it right. I'm telling you, class, that this particular dimensional analysis that I just asked you is just, let's say, 1 degree in terms of complexity of the next problems that you will be facing here in kinetics. So whenever we are discussing, please focus, and if you have questions, please ask questions because I cannot help you during the quiz if you do not know even to write the correct set of units. Majority of the items in your problem set are all something to do or has something to do with dimensional analysis. So if you have problems working on with this very simple way of expressing the set of units based on the rate, or rather based on the order of the reaction, I can see that you will have a lot to handle later on as we proceed. So I cannot, I'm already being upfront with you, I cannot be as bato-bato as I am right now because the topic that will be covered in kinetics is really voluminous. So please help yourself. Try working on the problems later. If you have questions, you ask me, but you have to process the problems there, of course, collaboratively with one another. Okay, so that's it for today. We will continue this Monday and Tuesday and already answer the items that you can answer based on what we have tackled already so far. Do you have any questions? So this is the answer that I'm looking for. So it should be liter squared per second per mole squared. Do you have any questions so far? I'll stop sharing. Okay, so if there's none, Let's call it a day for now. Work out the problems in your problem set there. You cannot still process the part wherein you have to do proving because that will still be covered on Monday. So we will discuss it on Monday and you can work it out after our class. Okay? So bye for now, class.